Hello everyone, we are Team 9 presenting the James Webb Space Telescope cooling systems by Manor Ahmed,
Fauzi Tattoo,
America Duarte,
Eric Gutierrez,
Jesse Chapa,
and Alvaro Torres.
The mission of the James Webb Space Telescope is to study and expand our understanding of the universe. It aims to investigate the formation and evolution of galaxies, stars, and planetary systems. It provides sensitivity and resolution in infrared wavelengths, allowing the exploration of deep space. This is made possible through the collaborative efforts of NASA, ESA, and CSA. One of the primary instruments of the telescope is a sun shield that helps to protect it from direct sunlight and manages heat through radiation discharge. Another instrument is a cryocooler, an active cooling system that is essential for maintaining low temperatures. Lastly, thermoacoustic heat exchange and pulse tubes are used to reduce the disruptions caused by vibrations.
Maintaining temperatures below 50 Kelvin is crucial for the James Webb Space Telescope to achieve maximum infrared sensitivity. At such low temperatures, the telescope's instruments can operate efficiently without interference from excess infrared radiation or thermal noise, which could compromise the accuracy of the observations. However, reaching and maintaining such low temperatures presents challenges, including the need to mitigate performance impacting vibrations. Cooling systems such as cryocoolers typically have mechanical parts that can generate vibrations, which can degrade the telescope's imaging and spectroscopy capabilities. To address this issue, engineers have designed JWST's cooling systems to minimize vibration transmissions to the sensitive instruments while still achieving the required temperature levels.
The sun shield is a vital component of the James Webb Space Telescope management system. The sun shield serves as both a thermal regulator and protector from harmful solar radiation. The sun shield manages heat through radiation discharge using advanced materials, which are Kapton, aluminum, and doped silicon for efficient heat dissipation and maintaining low temperatures. It also serves a dual role in ensuring optimal performance of the telescope's sensitive instruments. Firstly, it blocks out the sun's rays and prevents solar radiation from interfering with the telescope's observations, allowing it to focus on its targets in deep space. Secondly, by keeping the temperature of the telescope's components within a specified range, the sun shield ensures that the telescope can operate at peak performance and deliver precise observations of distant celestial objects.
Now for the sun shield and the function it has. Side, which is an instrument facing side of the sun shield, which maintains a temperature below 36 Kelvin to ensure optimal performance of the telescope sensitive instruments. A sun-facing side, which is the side of the sun shield exposed to sunlight, potentially reaching temperature as high as 380 Kelvin, which still effectively protect the telescope from direct solar radiation. There's also a temperature gradient, which is the significant temperature difference between these two sides of the sun shield. This also plays a crucial role in preserving the telescope's functionality and observational accuracy. The sun shield's design helps prevent temperature-related distortions that could impact the telescope's optical performance by maintaining a stable thermal environment for the instruments.
The cryocooler is an active thermal management system used in the James Webb Space Telescope to maintain the optimal operating temperature of its sensitive instruments, particularly the MIRI. The MIRI is designed to operate at extremely low temperatures near 7 K to ensure its high sensitivity and accuracy in detecting mid-infrared signals. The cryocooler plays a critical role in achieving and maintaining these low temperatures. The cryocooler utilizes a closed-loop system that circulates helium, a highly efficient coolant, to provide continuous cooling for the MIRI. This closed-loop system ensures that the helium is constantly recirculated, minimizing the need for additional resources and reducing the risk of contamination. The cryocooler's efficient circulation of helium helps maintain the necessary temperature stability for MIRI, enabling it to perform high-precision observations in the mid-infrared range without being affected by thermal fluctuations or excess heat. In MIRI, high-pressure helium gas is passed through a Joule-Thomson valve to generate a rapid cooling effect in ultra-low temperatures.
The thermoacoustic heat exchanger harnesses the thermoacoustic effect to enable heat transfer without any moving parts. The process involves filling a tube with helium gas and fitting stacks of parallel channels composed of low thermal conductivity materials at one end. Speakers placed opposite each other generate opposing sound waves at the tube's resonance frequency, forming standing waves. This creates a temperature gradient within the stack located at one of the tube's walls, with the point closest to the wall becoming hotter than the furthest side due to the low thermal conductivity of the material. The hot end connects to a heat sink, which releases heat into space while removing heat from the primary cooling system that uses helium as a working fluid. The thermoacoustic heat exchange mechanism offers several advantages over traditional cooling methods. By eliminating the need for moving parts, the mechanical complexity of the cryocooler is significantly reduced. This simplification results in increased reliability, as there are fewer components that could potentially fail during operation. Additionally, the thermoacoustic heat exchange mechanism requires less power to operate, leading to reduced power consumption for the overall cooling system.
In the design of the James Webb Space Telescope cryocooler, minimizing vibration is essential to prevent any potential compromise in the image quality and interference with the telescope's observations. To achieve this, pulse tubes are incorporated into the cooling system. Pulse tubes are a type of cryocooler that utilizes pressure oscillations of working fluid, typically helium, to transfer the heat without any moving parts. This design features help to minimize the mechanical vibrations that may be transmitted to the telescope, thereby ensuring stable and high-quality observations. The Joule-Thomson effect plays a crucial role in the rapid cooling effect achieved in the cryocooler system of the James Webb Space Telescope. This thermodynamic phenomenon occurs when a fluid undergoes a temperature change as it transitions through a valve or porous plug while being insulated from any heat exchange with its surroundings. High-pressure helium gas is passed through a Joule-Thomson valve. As the gas expands, the pressure energy is converted into thermal energy, generating a rapid cooling effect.
The sunshield challenges are ensuring that the sunshield effectively maintains a stable temperature gradient to prevent heat-induced distortions that could affect the telescope's performance, continuously refining the sunshield's materials and design to provide the best possible thermal insulation, reducing heat transfer between layers and the instrument-facing side, further enhancing the sunshield's ability to reflect solar radiation to minimize heat absorption and protect sensitive instruments from damage. The cryocooler challenges are ensuring the long-term reliability of the cryocooler system to maintain optimal instrument performance throughout the telescope's mission, developing advanced cryocooler designs and materials that can withstand the harsh conditions of space and operate efficiently for an extended period. And lastly, innovating cryocooler designs that effectively reduce vibrations that could compromise image quality or interfere with the telescope's observations, such as the implementation of pulse tubes and other vibration-reducing techniques.
All right, some of the research opportunities are exploration of advanced materials like graphene, carbon nanotubes, aerogels, and nanophones for improved thermal management, investigating microchannel-based cooling systems for precise temperature control and enhanced heat transfer, study of phase change materials for passive temperature regulation and reduced power consumption, examining alternative working fluids such as hydrophilic and ionic liquids for environmentally friendly and high-performance cooling solutions. All right, our conclusion is essentially the James Webb Space Telescope relies heavily on optimal thermal management systems to maintain its sensitive instruments at the required low temperatures for accurate observations. These systems, including the sunshield and cryocooler, ensure that the telescope can perform at its best, minimizing thermal noise and reducing potential heat-induced distortions. Sunshield provides passive cooling and cryocooler offers active cooling for precise observations. Advanced materials and engineering techniques contribute to effective cooling solutions. Continuous research can lead to improvements in thermal management technologies and materials. Lastly, effective cooling solutions are key to unlocking the potential of space telescopes and shaping the future space exploration. Thank you for listening, and our last slide will show you our references.